Канадського королівського наукового товариства, так само і члена Лондонського ліннеївського товариства. Доповідь Perfect Storm, Climate Change, Disease і ми буде представлена англійською мовою, але я просив, щоб це було дещо адаптовано для нашого. Якщо у когось потім після доповіді будуть питання, то ви можете їх задавати, навіть якщо ці питання будуть українською. Якщо можна, то англійською, але ми що-небудь придумаємо. Дякую за увагу.
First of all, I would like to thank you very much for the invitation. Even before 1989, there were a few things about this part of the world that North Americans knew, and one of them was this research institute and the history of the researchers in it. But when I was a student growing up in Washington, D.C., back in the Pleistocene, I never had any hope that I would ever see this place. And so it's a wonderful honor to be here on many levels. The problem is that today my job is to ruin your day and change your life, especially for the students. The good news is I will not be speaking in Hungarian. The bad news is I will not be speaking in Ukrainian. So you'll have to put up with something in the middle, which is American English, or what Americans call English. Now, the problem, okay? The problem is that there are a lot of diseases on this planet. And there are new diseases and outbreaks of old diseases in new places and in new hosts every day. There are websites like Outbreak.com that are just, if you want to feel like the world is coming to an end, just read Outbreak.com every morning. This is a long list. Today, the newest news today is that there's probably going to be a major dengue fever outbreak in the Caribbean this year. Oh, wonderful. But even worse than that is that now, when we hear news like that, we go, oh, yeah, it's another disease outbreak. And this is an indication of how great the problem is. We have diseases that are emerging on this planet every day. They are not just affecting human beings, they're also affecting the plants and animals that we depend on for food and for commerce. And these outbreaks are happening much more rapidly than our theories about the evolution of pathogen host systems would predict. So this is not just a problem for the world at large, for the practical world. This is also a challenge for evolutionary biology, because clearly we have been missing something. We failed to anticipate the emerging disease crisis. If you just read the newspaper reports, the news accounts, the online news accounts, you might have the impression that the emerging disease problem is just a problem that's associated with a few really nasty viruses in the tropics, things like Zika and Ebola and dengue. But the reality is that viral infections actually are the least expensive kind of pathogens on the planet. Bacterial infections cost the world much more than viruses every year. Helminths and protists cost the world more than bacteria every year. And we are now seeing old diseases returning. So malaria has now returned to southern Europe. Schistosomiasis has been reestablished on Corsica. And after 5 years, the public health people have decided that perhaps there's a non-human reservoir on Corsica that explains this. So we're very, very slow to react. We're very slow to understand what's happening. We're not anticipating. 3 years before the malaria outbreaks in Tuscany, southern France, and southern Switzerland last August, 3 years before that, a research group in Spain had published an article saying Anopheles mosquitoes are now capable of surviving the winters in southern Europe because the winter temperatures are mild enough. Nobody paid any attention. And in fact, when a 6-year-old Italian girl died in a hospital in Tuscany, the hospital spokesman said, "We don't understand this. This little girl never traveled outside of Italy, and we know there's no malaria in Italy. So we don't understand how this happened." This is the state of the world. This is the state of our preparedness now. They are everywhere. They're transmitted in everything we do. Everything we do as human beings can bring us into contact in one way or another, potentially with a pathogen. The same thing is true for our crops and our livestock. They're found in rural areas, they're found in urban areas, they're found in the wildlands, basically everywhere. They're in developing countries, they're in developed countries, they're in the tropics, and they're outside of the tropics now. And they're moving out of the tropics even faster than the tropics is expanding north and south. They are a national security problem for every country on this planet. They're a problem for water security, food security, public health security, sociocultural security, and this includes things like coping with migrants, and economic security, because every country in the world has budget problems right now. And any increased expense on the public health system or the agricultural health system means less money someplace else. And it's costly. It's much more costly than anybody associated with organizations like the World Health Organization or the Centers for Disease Control will admit in public. It took Eric Hoberg and Walter Wieger and me 6 months to dig out even a conservative estimate of how much emerging infectious diseases are costing the planet every year now. And a conservative estimate is larger than the GDP, the gross domestic product, of all but 15 countries. If Hungary wanted to pay the bill for the world's emerging disease costs for 1 year, it would cost them their GDP for 4 years. And the countries, of course, that are most heavily hit by emerging diseases are the ones that cannot afford it the most. They're the ones that have the least money. So there's a really, really big problem. If we are not already at a point where healthcare costs are unsustainable, we will be there very shortly, globally. There is no country on the planet that is not falling behind with respect to the amount of money they have to pay for healthcare, for diseases, for emerging diseases, and how little return they're getting for their money. So the question for evolutionary biologists, because one of the things we say in our book that's coming out next year is that it's nobody's fault but everybody's to blame. And the scientific community has a lot of blame. Evolutionary biologists in particular, as I said, we failed to anticipate the emerging disease crisis. And we failed to anticipate it because during the 1950s and 1960s and on, we created models of coevolution that kept us from recognizing what was happening when it was happening. So we not only don't understand why there's this emerging disease crisis, we don't understand why we're losing the battle. So what's wrong with us, the evolutionary biologists in the audience, people like me? The problem is that our scientific beliefs about the nature of pathogen host systems and the evolution and ecology of pathogen host systems does not correspond with what we're actually seeing today. So we have a very drastic mismatch between theory and observation. Now, in the 20th century, there were two major models of coevolution. There was a lot of activity. There was a lot of thought for 100 years about what we now call evolution. But by the end of the 20th century, those thoughts had coalesced into two major categories, or two major classes of coevolutionary models. One is called the coevolutionary arms race model, which developed in the United States, not surprisingly, in the middle of the Cold War, and so that's why it ended up being called the coevolutionary arms race model. And then more recently, there is John Thompson's geographic mosaic theory of coevolution. Now, the coevolutionary arms race model, which is usually associated with a paper in 1964 by Ehrlich and Raven in the journal Evolution, but which was actually described mathematically in a paper also in Evolution 6 years before Ehrlich and Raven published their paper, and they never cited it, by a mathematician named Mode. And the reason Ehrlich and Raven didn't cite Mode's paper was because Mode was working with agricultural diseases, and Ehrlich and Raven were working with butterflies and plants. Obviously, these things must not have anything to do with each other, and yet they both described exactly the same phenomenon. And that's one in which you have a theory of progressive specialization, ecological specialization, in the association between particular pathogens and their hosts, with the pathogens evolving traits to attack the hosts and the hosts counter-evolving traits to defend themselves from the pathogens. The geographic mosaic theory of coevolution allows the possibility of coevolutionary arms race interactions but doesn't require it. Okay, coevolution, in some ways it's a more general model. Coevolution, according to Thompson's theory, occurs when generalist parasites are distributed among multiple hosts in different places. Each of the hosts is assumed to represent a slightly different resource, slightly different selection regime, and when these different host pathogen populations are isolated geographically, you have the emergence of multiple new specialist pathogen host situations. Now, the interesting thing about this is that both of these categories of models agree on one thing. The pathogens are highly specialized on their hosts, and once a strong coevolutionary dynamic has been established, the longer the host and pathogen are associated with each other, the less the chances that that pathogen is going to be capable of moving into a new host. In other words, coevolutionary thought, as of the end of the 20th century, led us to believe that evolution was the best firewall we had against emerging diseases. Coevolution was going to keep emerging diseases at a minimum, because emerging disease requires that pathogens get into new hosts. And this led to, in the early 20th century, to what the insect plant people like Sal Augusta called the parasite paradox, or the pathogen paradox. There are not an equal number of generalist and specialist pathogens on this planet. There are not an equal number of generalist and specialist herbivorous insects on this planet. The vast majority of them are highly specialized, especially with respect to host range, that is the number of hosts utilized. But it also turns out that host range within groups of pathogens, including within groups of phytophagous insects, host range changes over time. And we have all of these emerging diseases occurring in real time. So something is going on much more rapidly and in a much more complicated way than our coevolutionary models of the 20th century suggested. Phylogenetic comparisons, which were not possible until the last 25 years of the 20th century, essentially, all of them have shown that pathogens moving around among hosts and changing their host range through time is actually the evolutionary pattern. This has always been the case. So we need a new paradigm of something. We don't even know what to call it. Well, we do. I call it the Stockholm paradigm because most of the insights that I've gained about it were done in conjunction with collaborations with the insect plant people at Stockholm University. So how do we resolve this paradox that pathogens are in fact highly specialized ecologically? Most of them at any one point in time in any one place have very restricted host ranges, but they're capable of moving among hosts really readily. Well, it turns out that one of the things we have to explain is this whole business about host range evolution. Okay, I'm not going to use the term host specificity because we don't believe that there is any such thing as host specificity. Just as I'm not going to use terms specialist and generalist because those are non-evolutionary terms. Organisms can specialize or generalize, but specialists and generalists can't. They are either one thing or another. And so they either exist or they go extinct. They don't diversify. And part of the problem we've had is the language that we've used. And the history of some of that language is quite interesting, and it was quite rational at one point in time, but it's not working. Okay? So here's what we find when we look at host range, that is, the number of host species and the phylogenetic breadth, the phylogenetic distribution of host species utilized by particular groups of pathogens or phytophagous insects. What we find is that over time, the host range expands and contracts and expands and contracts and expands and contracts. Now, we have a really good theory to explain how things that are generalized can become specialized. I mean, we know that really well. In fact, Darwin's entire theory was based on the assumption that everything is specialized in some way. Those were the adaptations. But what we've never had is an explanation for how something that was highly specialized could be generalized. So if evolution or coevolution is some sort of process of continually producing new specialists, where did the generalists come from? You might be interested to know that the concept of ecological generalists is only about 50 years old. Until about 50 years ago, it never even occurred to anybody that there could even be any such thing. It was an idea that was thought up to try to explain this problem of how do we get new specialists all the time. So what this oscillation is what the Swedes call the oscillation hypothesis. This phylogenetic pattern of host range is doing this in evolutionary time. What that implies is not only that generalized species can become highly specialized, but also that highly specialized species can become generalized. So that there's one general mechanism that explains both the host range expansion and the host range contraction, or the generalization and specialization, generalization and specialization. And it turns out that the key element to this is understanding a concept that Dan Jansen proposed in 1985 called ecological fitting. Basically what ecological fitting says is this: every species lives in a place doing something that works really well for where they live and what's available to them. But every one of those species could live someplace else as well. Now, in terms of pathogen-host associations, what that means is that even if a pathogen occurs in only one place and infects only one host in that one place, that pathogen will still be capable, without any new genetic mutations at all, is capable of infecting other hosts in other places. So that means that the capacity to live in multiple hosts is always present in pathogens that are highly specialized. Everything we measure about them in terms of their transmission dynamics, their microhabitat preferences are highly specialized, but their host range restriction, the number of hosts that they infect, is highly contextual. It's not a built-in genetic deficit. It's contextual. It's part of their ecology. It's part of their ecological context. And we can always assume that there are other species in other places that are susceptible to any pathogen, any particular pathogen, but are not infecting, the pathogen's not infecting those other hosts simply because they have never come into contact with each other. And one of the side products of that is that if you've never come into contact with a pathogen before, even though you're susceptible, there's been no possibility of selection for resistance in your population. So that means two things. If you ever come into contact with that pathogen will recognize you as just more of the same real estate and will immediately add you to its list of hosts. And you will have no resistance to it. And this is because, and as I said, we don't use the term host specificity anymore because pathogens are not specialized on hosts. They're specialized on traits that hosts have. So there's no conflict between saying that pathogens are extremely ecologically specialized and saying there's no such thing as host specificity. And the reason for that is because the traits that pathogens are specialized on are found in hosts. So of course there's some correlation between hosts and pathogens. But this is one of the things that the phylogenetics revolution showed us, was that there are a whole lot of ways that this can be true. For example, here's sort of the old-fashioned model of host pathogen associations. So here's host G, and up here this I, that one, that's the pathogen. And this is, the pathogen is restricted to the host. This is what we would call extreme host specificity. They are a very specialized pathogen. And what I've done here on the phylogeny of the host is I've made this line very thick. And that represents the phylogenetic distribution of the resource or resource base that the pathogens are specialized on. And in this particular case, because the pathogen is specialized on a resource that is only found in one host, that pathogen can only survive in one host. That pathogen still has the ability to move around if the host moves around geographically. But the pathogen is restricted to that one host. Now, what happens if that same resource now is distributed among 3 different species of hosts? It's the same resource. All 3 species of hosts have that same highly specialized resource because they're all closely related to each other. And that means that if this parasite, this pathogen, is normally only found in host G, if that pathogen ever came into contact with F or H, we would have to predict that it would immediately move into those hosts because, as far as the pathogen is concerned, those are not 3 different host species, they are all the same thing. Because what the pathogen is specialized on is characteristics of the host, not the host species. So in this particular case, we would say, oh look, the pathogen's becoming a generalist. No, it's not. It's still highly specialized. In fact, nothing has changed about the evolutionary status of the pathogen. All that's changed is the number of susceptible hosts that are exposed. Now here's a situation in which we have the same sort of deal. All right? So now we have 3 hosts that all have the same resource. In this case, that resource is very ancient. So the 3 hosts are not closely related to each other. But the resource that they share in common is a common evolutionary inheritance. They all have it for the same evolutionary reason. And in this particular case, you could have a situation in which the pathogen could infect all three of those hosts without becoming a generalist, without any kind of coevolutionary interactions at all, simply because all three of those hosts have the same resource. And it's a very specialized resource. You can also, of course, have a situation in which that same resource has evolved convergently. So it turns out that pathogen-host associations, once you understand that what pathogens are specialized on are resources of the host, which means traits, and you begin to look at the issue of pathogen-host association in terms of trait evolution, it turns out that, in fact, there never was any reason to believe that pathogens would be so locked into one host that they couldn't do anything. There is, in fact, the resolution of the paradox, the parasite paradox, is that highly specialized host traits can have a very broad phylogenetic distribution. And if the phylogenetic distribution of the host trait is greater than the geographic distribution of the pathogen, there will always be hosts out there somewhere that are susceptible right now if the pathogen only finds them. Oops. All right. Excellent. Now I'm going to have the point. No, don't worry about it. It's okay. We use a different lightsaber. Community have been lying to ourselves. Okay? This is an example that is found in a number of English language first-year evolutionary biology textbooks. And it is called an example of mirror coevolution, co-speciation. This is given as an example of host and parasite phylogenies being exactly the same, except it's a lie. I mean, it's a lie. It's just simply untrue. And in fact, these dots represent every place that there isn't co-speciation. And the dotted lines represent additional places where the pathogens have jumped into new hosts. And this is called the classic case of co-speciation. And 50% of this, I mean, this is actually pretty high for real data sets because almost 50% of the associations in this are the result of co-speciation. In most cases, it's not nearly that much. Okay. So second of all, is this issue of how a specialist, okay, how specialized species can generalize. In other words, it's not only a situation in which generalized species become specialized and then that's it. There is a mechanism whereby highly specialized species can generalize themselves. And that's allowed by what Sal Augusta has called sloppy fitness space. The recognition that fitness space, or all of the dimensions on this planet where a given species of any kind could exist if it were in that place, is in fact sloppy. Most of the potential viable fitness space for every species on this planet is unoccupied by the species. So this is an example. If you have 3 host species that all have the same specialized resource, but the pathogen only lives in a place where one of those species occur, you've got these 2 whole species of hosts out there that make the fitness space for the pathogen very sloppy. In fact, the pathogen's only occupying 1/3 of all of its possible fitness space. So it always has options, even no matter how specialized it is. And ecological fitting connects with this by recognizing that the fitness space for pathogens, okay, which includes all the hosts and all of the trophic interactions that are necessary to maintain a viable pathogen population. That includes hosts that the pathogens have used in the past, but don't use now. Pathogens, hosts that the pathogens are currently using, and hosts that the pathogens could use, but currently are not exposed. So that's the dimension of parasite fitness space. The so-called co-phylogeny studies are an interesting exercise in academic denial. The co-phylogeny studies, basically, the methods were developed to help us maintain the mythology that there was any co-speciation between pathogens and hosts, despite the evidence. The co-phylogeny studies are basically methods that are designed to allow you to believe that any amount of host switching is the result of cryptic co-speciation. The reality is that what co-phylogeny studies do is give us an estimate of how sloppy the fitness space is for any given pathogen. So, for example, if we go back to the lice and fleas, look at this. Here are the places where you have episodes of host switching, episodes of host range expansion in history. The first thing to notice, and we'll come back to this, is that, oh look, there's sort of co-speciation switching. It's oscillating. So you see evidence of the oscillation hypothesis here. And when you begin to look at the total range of hosts that are viable, given the known host switching episodes, you begin to realize that the potential range of hosts that could be occupied is enormous. And yet there is no indication that any of those fleas are anything except highly specialized ecologically. So this is not a situation in which we're producing lots of new specialists or anything like that. This is just a situation in which, given the opportunity, pathogens will exploit more of their available, highly specialized fitness space. So it's about opportunity. Okay? It's about new opportunities being introduced to hosts that are already susceptible, but you've never seen them before. It's not about the evolution of new genetic information. The expansion of host range as a result of ecological fitting and sloppy fitness space is what allows the possibility for a highly specialized pathogen to become much more generalized in fitness space, setting up the possibility of secondary specializations occurring after the fact. So the emergence of new genetic information that's very specific in specific places is a consequence of host switching. It's not a cause of host switching. And what creates new opportunities for pathogens? Oh God, it's climate change. Thank goodness I'm from the United States and there's no climate change in my country. Otherwise, we'd be in big trouble, like the rest of the world. Climate change is the single factor that we have found, and I'm going to show you a couple of phylogenetic studies. Every phylogenetic study we've done has found the following pattern. Not only is there no co-speciation, there's a lot of host switching, but the host switching doesn't happen periodically throughout time. The host switch happens in bursts. And from the molecular dating evidence and the geographic context evidence that we have, what we've discovered is that every one of those bursts of host switching, host range expansion in phylogeny, the host range oscillations, every one of those is tightly correlated with a major episode of global or regional climate change in the past. So that's the direct link between climate change and the emerging disease crisis. And we're still hoping that medical doctors and veterinarians will stop being creationists and start becoming real biologists and understand that they're dealing with an evolutionary problem. Because that's one of the issues we have right now, is that we don't have enough public and veterinary health and agricultural health people who understand that this is an evolutionary phenomenon at work. So the relationship between sloppy fitness space and ecological fitting is the relationship between opportunity and capacity. There's always potential opportunity for pathogens to occupy more geographic space and more hosts than it appears at any one point in time. And there's always the capacity to do that because the highly specialized host resources that pathogens require and the trophic interactions that are necessary to maintain the transmission of the parasite generation to generation are highly conservative phylogenetically. So they're everywhere. And that's what allows ecological fitting to happen. Now, this is still incomplete because the oscillation hypothesis at this point, when we add ecological fitting and sloppy fitness space to it, the oscillation hypothesis still basically says that a group will oscillate, the host range will oscillate, enlarge, get small, enlarge, get small, enlarge, get small, until all pathogens are maximally finely distributed among all hosts. And then it would stop. So at this point, we still have an incomplete explanation because we don't have any mechanism for the continued diversification of these groups of parasites. And after all, remember that more than 50% of the species on this planet are pathogens, so we really do need a general explanation for how these things diversify. And what drives that diversification? Well, it's climate change again. What drives the diversification is the opening up of fitness space, increasing connections among fitness space that were not there before, or changing the geographic distribution of fitness space. And that requires an external driver. That's not something that the parasites and the hosts do to themselves. So external perturbations drive the exploration of sloppy fitness space. I mean, it's that simple. What climate change does is climate change allows things to move around. That's all it takes. Things move. And when things move, they come into contact with opportunities that they never knew existed before. And if we're not paying attention, then those pathogens that are moving around are going to come into contact with us, our children, our livestock, our crops, and we're not going to be prepared for it, and the economic impacts are going to be devastating. So the final element in the Stockholm paradigm is the biogeographic driver, the external driver, this phenomenon called the taxon pulse, which Terry Irwin, an entomologist at the Smithsonian, actually proposed in the late 1970s and early 1980s, and it was ignored by the phylogenetic biogeographers. The taxon pulse hypothesis basically says that the geographic distributions of related species are the result of alternating episodes, oscillating episodes if you will, of host range expansion, isolation and speciation, then subsequent expansion and isolation. Expansion and isolation. And during the periods of expansion, the species are responding to climate change by moving away from deteriorating habitat into areas where the habitat is what they prefer. In other words, most of what happens when climate change occurs, species do not stay in one place and magically evolve adaptations to stay in that place. Mostly they run away. If it's getting drier, they move trying to find a wetter place. If it's getting wetter, they move away trying to find a drier place. And when these move away from here, these guys move in. Now, during periods of isolation, which are periods in which species are restricted or specialized in fitness space, that's when you have the possibility of evolutionary innovations occurring. So let's assume that you have one expansion event, and then you have an isolation event that splits that one ancestral species into 30 different species sometimes. And let's assume that in only one of those 30 places, the isolated population evolves some novel kind of ecology, some novel host. When the next episode of climate change occurs and all those isolated pieces of fitness space are reconnected, that one species with the new characteristic has 29 other places it can colonize without competing with any of its relatives because it's already different from its relatives. So you only have to have evolutionary innovations occur one every 30 speciation events in order to produce very complex ecosystems that are made up of things that have colonized each other multiple times, which is what we see. And this produces what we call reticulated area relationships. That is, all the species living in one particular place are not there for the same reason. They don't all have the same history with respect to how they arrived in that place. And that those histories are different histories of expansion and isolation, or generalizing and specializing, that sometimes are specific to particular clades and sometimes are parts of very general patterns, like general responses to major climate change events. So here's an example from some parasites. This has to do with an analysis of just two groups of nematode parasites in humans and great apes. It turns out that human beings, part of the story of humanity and our disease burden is that when we moved out of the forest into the savannas 2 million years ago, we probably only had about 10 or 15 different species of pathogens infecting us. Today, as a result of all of our human evolution, all of our amazing advancements, we have about 1,500 pathogens that we've acquired as a result of moving around, building cities, domesticating things. All those wonderful things we've done have always been accompanied by an accumulation of pathogens. So it turns out that if you want to do a deep history analysis of humans and other primates with respect to coevolution, you don't have many options. There just aren't that many groups of pathogens. And these are two of them, pinworms and hookworms. And this particular diagram is not a phylogeny of the hosts. This is a historical map of the distribution among hosts of the species of pathogens, of parasites in these two nematode groups. And the heavy lines, these thick lines, are the places where the pathogen and host relationships correspond with each other. And all of these thin lines are places where there was major host switching events. Now, the thing that's important about this is that these two groups of parasites are, again, supposed to be prime examples of a one-to-one correspondence between the host phylogeny and the parasite phylogeny. And it's about 40% that, about 60% host switching. And the interesting thing about this is that all but one of those host switches involves great apes and their closest relatives. So what you have is the host switching is not random. The new hosts that are being colonized are closely related. They're not sister groups. It's not a co-speciation thing, but it's more a co-phylogeny thing. The pathogens the hosts are closely related enough that they have common resources that the parasites recognize, but they're not each other's closest relatives. So with one exception, all of those host switches are the result of ecological fitting. So conditions changed, hosts moved from one place to another, bringing their pathogens with them. The pathogens met another host that they liked just as well, and so they decided to infect them too. So now let's look at the hosts. And the great apes, so the hominoids since the Miocene. It's about the age of these parasite groups. But we're not going to look at just the hominoid hosts. We're going to look at the hominoid hosts with respect to two other groups of vertebrates that they're highly associated, that hominoids are highly associated with in the fossil record, the elephants and hyenas. And what's it look like? Well, it turns out, this is not a phylogeny of areas. Okay? This is a map of the geographic distributions of hominoids and elephants and hyenas since the Miocene. And every one of these thick lines, and in fact the thin lines are so small you don't really see them here, but there are a couple here and there's one here and one there. Those thin lines are places where only one of those three groups of hosts did something that the other two groups did not do. So even though this is very complicated, it's a complicated history that was shared by humans and elephants and hyenas and presumably all the plants they were eating and lions and tigers and everything else. So this is just a little exemplar for a larger system. And it turns out that what the summary of that picture is the following. What you have is out of Africa into Asia, isolation in Asia, out of Asia into Africa, isolation in Africa, out of Africa back into Asia, back and forth and back and forth. That explains, for one thing, that explains why the steppe habitats of Central, Eastern Europe and Western Asia, Eurasia, that's why the greatest diversity and abundance of elephant fossils are there, because that was the highway. They went back and forth, and that was the area that experienced the largest number of movements. West to east to west, west to east to west. So if somebody says, so what do you believe about human evolution? Out of Africa or out of Asia? And you say, yes. Yes, indeed. And it turns out that this is a very old, this is a 12 or 15 million year old pattern. But it turns out for the last 15,000 years, human beings have been doing the same thing. Every time the climate has changed in the last 12 to 15,000 years, human beings responded to climate change by moving away if they could, coping with the changed situations if they could, and dying if they couldn't. And that's kind of the story of evolution. So it turns out that what we would expect to find is clusters of host range expansions that are correlated with climate change events. And that's exactly what we find in all of these studies that have been done so far. So the Stockholm paradigm is a dynamic hypothesis about the interplay between capacity and opportunity, in which changes in ecological opportunity drive the system and allow the subsequent evolution of new capacities. This is one of the reasons that disease emergence can be so rapid. We don't have to wait for some new mutation that allows the pathogen to jump into a new host before it happens. And that's why you can have these really rapid breakouts of disease. Once a new host has been colonized, has been added to the repertoire, the pathogen is then more generalized in its fitness space, and that allows a greater possibility for those kinds of strange new mutations to show up. This is one of the reasons that we understand that the geographic distribution of disease is always less than the geographic distribution of the pathogen. And we also know that the outbreak of disease, especially highly pathogenic versions of the disease, are almost always associated with the margins of the geographic distribution of the pathogen, because that's where they're expanding into new fitness space and coming into contact with susceptible hosts that have never seen them before and therefore have no resistance. So evolutionary biology, basic evolutionary biology, is important in trying to cope with the crisis of emerging diseases. As host range expansions are going to occur, that is, generalizing by highly specialized pathogens, will occur wherever and whenever geographic distributions and or trophic connections are altered. And the drivers are climate change and secondarily now human population, especially population density, and globalization. I mean, one of the worst things that humanity ever did to itself with respect to disease was to urbanize. In 1918, 100 years ago, this coming November, the so-called Spanish influenza pandemic infected 25% of the human beings on this planet. And it killed 10% of all of the humans on this planet. Influenza is a pathogen that is transmitted directly, and so the probability of transmission is directly proportional to population density. We currently have 4.5 times more human beings on this planet than in 1918, and 4.6 times as many people living in cities as in 1918. And we have not been able to reconstruct the variant of influenza that caused that pandemic. So it's not one of the variants that's included in any of the annual vaccines. We don't know what happened. We literally don't know at a molecular level what that was. But we do know, we know, that the ecological conditions, the opportunity for a much more devastating influenza pandemic exist. And we've created those conditions for ourselves, and we've made them worse by everything that our cities have done, like heavy industry, that has altered the trajectory for climate change. So it's like I said, it's nobody's fault, but everybody's to blame. I mean, nobody intended to do this. Everybody thought they were doing something good, and we really hurt ourselves. The pathogenicity is not caused by genetic changes, caused by climate change. That's because it's just a matter of susceptible hosts with no resistance. Well, let me not worry about that. We've already talked about this. We have to assume that there are many, many, many potential disease outbreaks waiting to happen. And remember, we're talking about not just diseases in humans. We're talking about livestock. We're talking about crops. Some of you may know that there's a rust fungus that's broken out in the Middle East that is moving north and west that does not respond to any known fungicide. Agricultural economists in Europe are now talking about the economic and nutritional impact of the extinction of wheat within 20 years. It's 27% of the calories that human beings eat every day on this planet is wheat. Wheat, rice, and corn, 3 species of plants. 67% of all of the calories that human beings eat every day. We've done this to ourselves. I mean, wheat, corn, and rice, we focus on them because we can get big yields out of them. But part of the cost of growing big yield crops is that they're highly susceptible to disease. So this is how we create this minefield of potential disease outbreaks. They can happen rapidly, they can happen quickly. We have to assume today that what we are seeing today is only the beginning of the really bad emerging disease crisis. What we're seeing today is nothing compared to what 30 years from now will look like. And we have no reason to believe that the host range expansions will stop until climate change fluctuations stop, and we don't know when that's going to be. Climate change fluctuations are not going to stop for the foreseeable future. That is, not for the next 100 or 200 years. So this is essentially a permanent condition, especially if you have children or grandchildren. It also turns out that what we're seeing with the Stockholm paradigm and pathogens and hosts is not restricted to pathogens and hosts. In fact, it seems that this is exactly what has happened to all of life on this planet evolutionarily every time there have been major climate change events. And this is a passage from one of Alicia Stegall's work dealing with periods 500, 600 million years ago. And the pattern is the same. The environment changes as a result of climate change. Species try to move away from the environment that's changing in ways that they're not adapted to. If they can move away and find good environment, they will survive. If they don't, they will die. The vast majority of extinctions are the failure to escape. If you're not able to expand into new fitness area and survive long enough to come up with a solution to the climate change, you'll die. And that's why we have episodes of 50 or 60% of the world's biodiversity going extinct during major climate change events. Because as Darwin pointed out, you can't always get, oh no, that's right, there was the Rolling Stones that said you can't always get what you want. But Darwin said it first. That basically, Darwin said, you know, just because the environment changes doesn't mean you magically get to adapt to it. Usually you don't. So this thinking, this paradigm, this Stockholm business, can be applied to a lot of different things because host range expansion, geographic expansion, it's the same phenomenon we talk about when we talk about invasive species and introduced species, and why sometimes introduced species do really well. It's the same thing we talk about when we try to understand why biological control programs so often fail. But the good news is that ecological fitting also explains why we don't necessarily expect entire ecosystems to completely collapse when key species go extinct. So this idea of a trophic cascade, you knock out a few keystone species and everything collapses, that will happen if there's no such thing as ecological fitting. If there is ecological fitting, then when this species goes extinct, we suddenly discover that this species here would have done this if this species had never been there. So this species goes extinct, this species just moves over and goes, ah, I'm glad that guy's gone. And it turns out then that maybe we don't have such catastrophic ecosystem collapses as we're worried about. So the news is not all bad. It's mostly bad, but it's not all bad. We have to understand that the period of time that we're living through now is one of these evolutionary episodes, and it really doesn't matter who caused it or what caused it. We are in a period of time, one of those evolutionary episodes in which the old is passing away, and it's setting the stage for the new to emerge. And the emerging disease crisis tells us that the biosphere is beginning to cope with climate change the way it always has. But we have to understand that biological evolution does not care about any particular species, no matter how self-important it is. The reality is we get to choose whether we're going to go extinct or not. The biosphere is simply going to cope with climate change, and we can decide whether we want to be part of that or whether we just want to pretend that there's no problem, and then we die, and it's not a problem because I'll be dead before my grandchildren have any problems, so who cares, right? Well, it turns out that there are things we can do if we decide to do it. Okay? So we have to start with this notion that we need to do something that human beings are capable of doing, but never do very well, which is we're always capable of anticipating the future, But rarely do we do anything about that. Okay? I can anticipate that because of my ancestry and because I'm fat, that I'm at risk for a heart attack. Am I losing weight? Right? So, all human beings are not particularly good about acting on the future. But we're in a situation now where if we as a species don't act on what we're anticipating, the results could be devastating. The time is short, the danger is great, and we are largely unprepared. By 2050, the World Economic Forum estimates that 100% of all agricultural soils on this planet will be completely depleted. We will be growing food hydroponically by 2050. The Melbourne Sustainable Studies Institute estimates that by 2050, a combination of conflict, migration, disease, starvation, flood, and drought will have eliminated the human overpopulation problem because half of the human population of today will be gone. That we will be from 7.5 million down to less than 4 million, 4 billion people by 2050. But bear in mind that because more than 50% of human beings live in cities now, and that's where all of our technology is centered, if we lose 50% of humanity abruptly in the next 30 years, we're going to lose substantial amounts of our technological infrastructure. So they anticipate that by 2050, living conditions on this planet will resemble the beginning of the 20th century. This is not good. I mean, this is really not good. And I don't know about you, but I have children and stepchildren and grandchildren, and all of them, like I have three wonderful Hungarian stepsons. And if I drop them in the middle of Beijing tomorrow with their cell phones, they could survive just fine. But if I take them out into the forest in the northern part of Hungary without their cell phones and say survive, they're dead. Because one of the things we've done by making ourselves urbanized, an urbanized species, is that we have created at least two generations of people now who find it almost impossible to live outside of a highly technological niche. When Hurricane Katrina ruined the city of New Orleans 10 years ago, within 72 hours of losing electricity and transport into the city, people were killing each other for food. And these are some realities that we have to face, and we can change that. With respect to emerging diseases, we have to be proactive. We have to stop waiting until the next big outbreak happens and then heroically respond to it. Because, let's face it, my doctor is right. If I lose weight and do not have a heart attack, that's going to be better for me, and it's going to be cheaper for the healthcare system than if I stay fat, I have a heart attack, and they have to save me with coronary bypass surgery. And then I have to change my diet anyway. So I might as well do it now, right? And save some money. Most of the money, that $1 trillion a year that's being spent on emerging diseases, is not spent on huge global pandemics, like the ones that Bill Gates is warning about now. All of those are what we call death by 1,000 cuts. A little bit here, a little bit there, a little bit here, a little bit there. That completely preoccupies all of the existing resources of agriculture and public health systems worldwide, which means that when a big pandemic happens, there aren't any resources left to deal with them. And we're not planning for this. We're not anticipating it. The world's public health and veterinary and agricultural health people act like the next report of an emerging disease is the last one that will ever happen. And it's partly because they've been trained in a paradigm of coevolution that is manifestly not true. What we need to do now, and it's with emerging diseases, you could put in food, water, warming, sea level rises, any of the threat multipliers for climate change in there. What we need now is policies that anticipate the future. We have to anticipate that things are going to get worse for us. We have to accept that, and then we have to adapt to what's coming. We can no longer afford to pretend that either nothing's happening or once it happens, we can fix it. Because the only way we can fix what's coming at us is to adapt to it. We will not magically come up with the right adaptation. When the Greenland ice sheet falls into the Atlantic Ocean, New York City will have 3 hours to evacuate. They are not going to magically come up with a solution at that point to save themselves. They will die. We are already moving into a world where there are two kinds of places for human beings. The places that people are running away from and places that people are running to. And both of those situations have severe consequences for our future as a technological species. We need to try to buy time. We need to try to adapt to what's coming and to accept what's coming. With respect to emerging diseases, we need to do what we call finding them before they find us. We need to know what's coming. If there's malaria in southern Switzerland, there is nothing to keep that malaria from coming through on a straight line through southern Austria, right to Lake Balaton in Hungary within 3 years. So, what do you do about it? What do you do? Well, it turns out that the answer is both simple and really complicated, because we have a protocol. We know what to do. We know how to get people out there, citizen scientists working with highly technologically people, and all this good technology and stuff. We know how to get out there and find this stuff and track it as it's coming towards us. We know how to teach people how to mitigate the possibility of getting malaria by doing things like looking for mosquito larvae in the bird bath in your garden and dumping them out. We know how to do that. There are a lot of things we can do. The problem is, this requires a degree of cooperation among human beings that humanity has never done before. I mean, in particular, doing something to protect your country from emerging diseases requires that you help the countries that are the sources of those diseases coming at you, even if you don't like them. So, for example, Hungarians sort of don't like anybody, but they mostly don't like people coming from parts of the world that used to occupy them. What a surprise, right? You used to occupy our country, we don't like you anymore. Well, this is not unreasonable, right? But it also is something that we cannot afford as a species. This is going to be very difficult. And I would say that most scientists would never say this in public, but when they're talking among scientists, they will say, we don't think that's going to happen. And this is what we call the Cassandra collective. Okay, so the myth of Cassandra. Cassandra was the sister of Paris who stole Helen of Troy and started the whole thing up. Well, when Cassandra was a priestess of Athena, Apollo tried to seduce her and she wouldn't let him. And so he cursed her. He said, I'm going to curse you. I'm going to give you the curse of true prophecy. Everything you say will be true, but no one will ever believe it. And so she was the one who said, I really don't think you should bring that wooden horse inside the city. And clearly that's a motif. Okay, the reason there's a mythical figure like that is because 3,000 years ago, human beings recognized that there were always people in their society who saw what was going to happen. and warned about it, but it seemed so strange that nobody would listen to them. And so when we say, you know, it's easy for a scientist to say, okay, time for all the countries on the world to cooperate and not be enemies anymore. I mean, that's a typical scientific statement, right? Now, in the real world of social science, you know, all of our social science colleagues just go, what is wrong with you scientists? This is not going to happen. We have, you know, give us something we can work with. But we are rapidly approaching a point where if we don't do something, something's going to happen anyway. And the biggest issue, we have a focus group on sustainability in Keurig at the Institute for Advanced Study in Keurig. And there is an emerging sense that the most important element of sustainability now has nothing to do with growth or development. It has to do with survival. And 10, 15 years ago, nobody doing sustainability work was thinking about sustainability in terms of basic human survival. Now that's what we have to think about. We have to start with, what do we need in order to survive? Well, the reality is, in a highly technological, highly interconnected, highly globalized world economy, individual places, no individual place on this planet is self-sufficient. So we either cooperate globally, or we find networks of cooperators. We find networks of people that we can cooperate with. But countries that decide that it will not happen to them, as far as we're concerned, are dead. And sadly, that includes my country. Right now, NASA estimates that the drought that is beginning in North America will last until 2050. So that date keeps coming up, right? And by 2050, the United States will have lost between 35 and 65% of its food production. If it loses 35% of its food production, it ceases to exist as a global economic entity, because that's what the United States economic, all of its trade is based on food surplus. Plus, all the countries that rely on American food surpluses will be faced with severe food shortages. If it's more than 35%, the United States will be in a position where it will need to beg food from all the many friends it's been making for the last 30 or 40 years on this planet. This is not a good situation. The American national strategy for dealing with emerging diseases is, and I kid you not, it will never happen here. That's their plan. That's why they're denying that there's Zika in North America, even though there are Zika babies in 44 states out of 50. That's why they're denying, they're saying that Zika is a mosquito-transmitted disease, when it is primarily a sexually transmitted disease that can also be transmitted by mosquitoes during the summertime. They're in denial, and it's going to kill them as a culture. They're in denial about disease, they're in denial about food production, they're in denial about sea level rises. The storm that devastated Houston, Texas last summer, that was a 7-meter sea level storm surge. That's equivalent to a 7-meter sea level rise, except it would be global and forever. 120,000 years ago, this planet had the same amount of carbon dioxide in the atmosphere as it has now, and it was the same temperature as it is now. And sea levels were 7 meters higher than they are now. The specialists who work on sea level rise problems are really worried because they don't know why the big one hasn't happened yet. They don't know what the planet's waiting for. And the longer this goes, the warmer things get, the greater, without some big release, greater the possibility that it's going to be a catastrophic change when it happens. And if this, if this is all happening at more or less the same time in the next 30 years, we really are not prepared to survive, which is terrible because we have all the ability to survive if we want to. I mean, all that technology in these cities that could be at risk is exactly the source of policies and programs that could enable us to survive. So mostly what I'm doing these days is just trying to beg humanity to save itself. Because, like I said, I have a daughter, I have some Hungarian stepsons, I got some American grandchildren, and I actually care about them. And in some strange abstract way, I would feel really bad if I lived long enough to see that before I died, things were going to be really bad for them. I would feel somehow responsible for that as a scientist. So evolutionary biology is really, really important, but nowadays there is no kind of basic biology, no kind of basic science that can be done without thinking about the consequences of global climate change and what we need to do about it. So I know I've dragged on long and I've made you, like I said, I was going to ruin your day, but hopefully for some of you, I will have helped, especially for graduate students, I've helped give you some ideas for how you might change your life and things that you might do to try to ensure your future. Thank you. So now everybody needs a drink. Or you're just, either a drink of vodka or a drink of hemlock.
Бачите, думки літають аудиторії, як і інститутом, прямо як вірус. І у нас питання впливу змін клімату на нашу країну і на людей піднімалось вже років 10 тому Леонідом Івановичем Францевичем. І дуже жаль, що його тут немає, тут було про що поговорити. Але, будь ласка, ваші питання. Anything clear? Саша.
This is exactly right. Suppose we have, imagine a conservation biology project in which you want to reintroduce a species that has gone extinct in part of its range, and you're going to reintroduce it. How many programs for such reintroductions incorporate the likelihood that the reintroduction is going to increase the chances of disease? Nobody. Okay. Now, one of our good friends in Budapest, Gabor Foodbody, he works with ticks and tick-borne diseases, acarologist at the vet school. And Gabor, in Budapest, there's a big island in the middle of the Danube called Margaret Island. And it's a recreational area, there's sports clubs there are rock concerts there are tourism, it's a major tourism site, major recreational area for people. Gabor began looking at the ticks on the hedgehogs on Margaret Island. And he discovered that the abundance of ticks on hedgehogs on Margaret Island is 10 times higher than in the forests. And not only that, but all of those ticks are loaded with rickettsial pathogens. But there hadn't been major disease outbreak on Margaret Island, even though there was this, the people were wandering in a soup of disease. Why not? Well, it turns out that most of the island, most of the public places, the grass is cut short. And so the ticks don't have tall enough grass to climb up on and wave for hosts. The only place they can do that is in the forested areas, the areas where there are trees, where they don't cut the grass. Okay? So if you don't go into that part of the park, you're never going to come into contact with a tick that could give you Rocky Mountain spotted fever or one of these other tick-borne diseases. But the government of Hungary had only 2 public toilets on Margaret Island because they were worried about people having sex in public toilets. Especially gay sex. They were so worried about that, there were only 2 public toilets on the entire island, and they were only open from 9 in the morning until 5 at night. And Gabor said, look, the reality is that gay sex in public bathrooms is a lot less of a problem than ruining your entire tourism industry because Budapest becomes known as a place where you can go into the park and die. So now there are public toilets all over the island. And it turns out, I mean, the government paid attention and understood that the immediate cost of putting extra public toilets out there was tiny compared to the cost of a major outbreak that could, you know, people getting sick during a rock concert, boom, nobody ever comes back. And that's a major part of their, I mean, tourism is a major part of Budapest's economy. That's a major part of Budapest's tourism industry. And so the government understood that this was something that would cost them a small amount of money now to make sure that they would never have to pay a huge price later. And it's the best example we know of this kind of thing. But the problem is that if that's true for ticks on hedgehogs on Margaret Island, it's true for every city on the planet that's trying to increase the green space in the city. I was in Brazil at the end of February, and I gave this talk, and 3 people came up to me just like this, and they said, we've been hired by Brazilian cities to design to make them greener. And you're telling us this? And I said, yep. And they said, well, that probably explains why São Paulo, which is a city of 20 million people, just closed all of its city parks because of yellow fever and malaria transmission. They've closed all of their city parks. So there's nothing we can do that doesn't have some, there's nothing we can do to try to make things better that doesn't also have potential costs. This is another, really important evolutionary principle. Everything that happens in evolution has costs as well as benefits. And if we only think about the benefits, that's what's happened with biological control. Nobody ever anticipated that the biological control agent could be released in a new place and find a local host that it liked better than the target host. And it keeps happening over and over and over and over again. And we keep thinking, next time it'll be okay. Next time we have it figured out. But there's all this potential and green spaces in large cities for all of the benefits that they're going to provide, the ecosystem services, right? One of the ecosystem services is an increase in zoonotic disease potential. So actually what we should be doing is we should have no green spaces inside central cities. We should have free mass transportation out to the periphery, and all of our green spaces should be out there. And we should make mass transit free to people to encourage them to go out and relax in a green space. But the more green spaces we intersperse in our cities, the more we're increasing the chances of zoonotic disease outbreak. And that's going to offset the extra oxygen the trees are producing.
More questions? Yeah.
May I ask, very impressive talk, but are there any recipes what country or government have to do? Because everything looks very scary. What we have to do? First step, second step, third step. Are there any programs elaborated how to mitigate all situation? Like
Yeah.
software, like it's not so.
Well, it's a two-part answer.
Yeah.
Okay. The first part of the answer is that there's a very well articulated protocol, what we call the DAMA protocol. But the bad news is that it's not being implemented anywhere. And we're in this funny, what we call a catch-22 situation. So for example, Gabor and I and some other people were in Munich in April. We were going to try to apply, there's an EU program called a COST program, which is a grant. Basically, that's money that the EU would give EU people to build a network of researchers to then get the big money to do a program. So we were going to do this, get the money to bring together a network of researchers. And they do it this way because the initial money can only go to EU members, okay, all the people on the grant. But once the EU gives them the money, they can bring in people from anywhere in the world to be part of their network of specialists. Then you have a global network of specialists who will increase your chances of success with other grant proposals. And we wanted to do this with DAMA. And one of the people who was there is a guy from Norway who's part of the One Health network. You know, he's very highly placed in the One Health thing. And he said, look, this is wonderful, and this is exactly what we need to do, but I'm telling you right now that nobody who's going to review these proposals knows what the DAMA protocol is. And the reason nobody knows what the DAMA protocol is because the book that we wrote that was supposed to be published by now is not published. And the reason for that is because we submitted the manuscript last June, almost 1 year ago. A month later, the science editor at the University of Chicago Press left to become the director of the Princeton University Press. The University of Chicago Press took 10 months to hire a new science editor. And during that time, none of their science projects could be approved to go forward. So we were getting reviews saying, you've got to publish this now, you've got to publish this now, this is really important stuff, you know. So now it will come out sometime in 2019. And so the guy from Norway, who was at this meeting in Munich, said, there is no point in applying for this grant this year. It will not get funded because nobody knows what you're talking about. If the book is published next year and is out for 2 or 3 months before the deadline for the grant, then you can submit it next year, and then the reviewers will have some idea of what you're talking about. So this is a situation, we even talk about this in the book, about how bureaucracy is killing us. I mean, the problem with bureaucracies are wonderful as long as nothing changes. I mean, how many of you have gone to, something, some simple part of bureaucracy like the post office or any kind of government bureaucracy, and you start to say, I've got a little bit of a problem. Instantly, the body language is like, so if you go in and say, here's the protocol, I followed the protocol, here it is, oh that's great, here's the receipt, blah, blah, blah. Bureaucracies are designed to be very rigid. That's the essence of their efficiency. So bureaucracies, and we are a bureaucratized species now. Bureaucracies are terrible at responding to changes. And that's this particular situation. The managing editor at the University of Chicago he does not understand why we're upset, because in his mind, they've done a really good job. We're a really important press, so we should take a long time to make sure we get exactly the right person. And we're going, if things are going to go terribly wrong within 30 years. You have just cost us 3% of the time that we have left. You know, doing your due diligence and making sure you got exactly the right person. And that's because if you're, you know, if you're at the University of Chicago Press, all this climate change stuff is very abstract to you. Your life is fine. I mean, in fact, the winters are a little bit warmer in Chicago, so everything's good. You're not seeing any shortages in the grocery stores. So you know, that's it. So yeah, we know exactly, this is the frustration. We know exactly what to do. And as soon as somebody decides, it's like we built a Ferrari, but we have no gasoline, right? As soon as somebody starts to pour gasoline into the tank, we had a workshop at Lake Balaton last October, and there was really broad agreement that this would work. This is how we do it, and it's a combination of working with local people in local villages and networking with specialists, science specialists, and policy people. Yeah, and I'll talk about this in Ascania. My talk in Ascania will be about that protocol, because that's where you have to talk about it, is out in the local people.
Sasha, more questions? No?
Yeah.
It sounds a little bit like we're just expecting the last season of Game of Thrones. That's how your lecture sounds. We really are expecting what will be in the soon, and early or later, everybody will die. Is it correct?
Okay. Here's what I want. Okay, I want us to react to possibilities the same way your military does. The same way the United States military is the organization in the United States that spends more money on climate change data from the National Research Council than any other organization in America. And I guarantee you that every organized military in every country on this planet has contingency plans for, not just for climate change in particular, or in general, but pandemics, sea level rise, big storms, and all these sorts of things. And nobody thinks that it is a waste of money for military people to anticipate problems